So as I said in the last clip, the complex numbers look just like the plane R2, but now we have a way to multiply these vectors together. So let's draw a picture. So we've got, here's a picture of the plane, R2. And so we have two axes, like I said, so I'll call that the real axis, and this one the imaginary axis, like that. And then a complex number is a thingy that looks like a real number plus I times another real number. And so we can think of that as having a real coordinate of A and an imaginary coordinate of B, like this. And so this A plus IB, this is the same thing as the coordinate pair AB on the plane. And in fact, if you learned about basis and basis vectors in your previous linear algebra class, then you can think that the standard basis for the plane here has a vector 1 on the real axis, which is shorthand for the point with coordinates 1, 0. And it has I on the other coordinate, and this is shorthand for the point with coordinates 0, 1. And so this is just a renaming of the standard basis. And so here, R2, whoops, is the, I'll use the blue notation when I'm thinking about it as R2, and the black notation when I'm thinking about it as the complex plane. And so, like I said, we can multiply vectors together. Now, you might have seen how to do a dot product of two vectors, or in R3, the cross product of two vectors, but I'm talking about something different here. So this is, we take the point AB and we multiply it by the point with coordinates CD, and what we get is the point with coordinates AC minus BD and AD plus BC, which looks like a bunch of crazy nonsense, and in fact you should not memorize this. There's no point to doing so, and it's probably just confusing. The reason why you don't need to memorize this, and the reason why that multiplication rule, where it comes from, is just from distribution. So if we go back to the complex form of thinking about these numbers, and we recall that I squared is equal to minus 1, and we just distribute this thing with good old FOIL, then we get, let's see, so we've got AC plus ADI, and then we've got BCI plus BDI squared. And then, of course, that I squared just becomes a minus 1. So if I group the real parts together, I have AC minus BD, that's the real part. And then I can factor the I out of AD plus BC. And you'll see that that matches with this one that we had before here. But you don't have to remember the formula, you can just FOIL it out. Also, with complex numbers, there's another operation that comes up from time to time. We might not use it a whole lot, but it's still handy to know about for doing algebraic or arithmetic simplifications. It's called the conjugate. And so the conjugate of a complex number, so let's say A plus BI is a complex number, then the conjugate is denoted with a little bar. And what we do is we just flip the sign on the imaginary part. So if it was A plus BI before, it would now be A minus BI. And geometrically, what this corresponds to is, let's see, so let's go back and we look at our point a plus bi right here. So there's a, there's b on the axes, and so this point right here is a plus bi. Then the conjugate is just flipping around the horizontal axis. And so this is a minus bi, because of course this is minus b down here. And so then that means that, for example, if you want to know the magnitude of the complex number, so the distance, the length, how far it is from the origin right here, then the magnitude of a plus bi, well, we can actually see this by multiplying the number by its conjugate. So if we do c times c conjugate, so that's a plus bi, a minus bi, then when you work this out, you get a squared minus negative b squared, in other words, plus b squared. But a squared plus b squared, that is the square of the length of this guy right here, yeah? So we call that the square of the length of c. Okay. And so from now on, we're going to write complex numbers always in this notation, the a plus ib, and no longer in the coordinate notation, because we're going to be looking at vectors. So things where there can be, multiple complex numbers as entries of a vector, and it would just be terrible to have all those parentheses. So we'll write it that way.